Let's discuss some of the interview questions on Java for software engineer role in IBM. For in-detail explanation, pause video and go through images. Let's start. What are sealed classes in Java and where would you use them? Sealed classes provide restricted inheritance, meaning they allow you to specify exactly which other classes are permitted to extend them. This limits the inheritance hierarchy to a fixed, known set of subclasses. For example, if you declare a sealed class shape that only permits circle and square, no other class like triangle can extend shape unless explicitly allowed. There are two main benefits. First, they help in controlling class hierarchy. By ensuring only permitted subclasses, you create a finite, manageable set that prevents unauthorized extensions. This is perfect for domain modeling, such as representing states or payment types. Second, sealed classes improve code security and maintainability. They limit exposure and potential misuse, and they facilitate exhaustive pattern matching in switch expressions, allowing the compiler to know all possible cases and leading to robust, predictable code. To use sealed classes, add the sealed modifier on your base class. Specify permitted subclasses in a permits clause. Each permitted subclass must be marked as final, sealed, or non-sealed. Subclasses must be accessible in the same module. Let's move to next question. How do stream.peek and foreach differ in behavior? First up, peek is an intermediate operation, mainly used for debugging or inspecting stream data. It lets you perform actions such as logging or printing the stream elements without actually changing the contents of the stream. After peek runs, the data continues to flow through subsequent stream operations unchanged. On the other side, foreach is a terminal operation. It's used when you want to perform an action on each stream element, like updating a database or producing a final printout. Unlike peek, foreach can alter the state of the external system or have other side effects, such as generating output or changing data. So, in short, peek is intermediate, non-interfering, and built for observation and debugging only, and foreach is terminal, state-altering, and used for final actions that may affect external state or produce side effects. Let's move to next question. Explain the concept of immutable collections introduced in Java 9+. Java 9 introduced immutable collections that do not allow structural modification. Once these collections are created, you cannot add, remove, or clear their elements. This ensures that your data remains constant after initialization. An important advantage is thread safety. Since these collections never change, multiple threads can access them concurrently without explicit synchronization. This reduces the risk of bugs linked to concurrent modifications. Let's compare legacy mutable collections found before Java 9 against the new immutable ones. Mutable collections can change after creation, which brings the risk of accidental modifications and thread safety issues. Immutable collections, by contrast, offer a guaranteed constant state. The data stays predictable and secure throughout the application's lifecycle. Immutable collections are perfect for storing read-only configuration data, such as API keys or application settings. You can safely share this data across your application, and it remains stable from start to end, making it globally accessible and reliable. Let's move to next question. What is the difference between list.off and arrays.asList? List.off allows you to create an immutable, unmodifiable list. Once created, you cannot add, remove, or update elements. Any attempt triggers an error. All elements must be non-null, and the storage is internally optimized and inherently thread-safe, making list.off perfect for defining constant collections, configuration settings, or values that must never change. On the other hand, arrays.asList creates a fixed-size list backed by the original array. While you can modify individual elements, meaning changes affect the underlying array, you cannot add or remove elements. This method allows nulls, but it is not thread-safe. It's useful for bridging legacy APIs or when you want to update list values without resizing. So if we compare both, list.off is truly immutable, does not allow nulls, and is safe for concurrent use. Arrays.asList is mutable in terms of element replacement, allows nulls, and shares changes with its backing array. Neither method allows resizing. List.off appeared in Java 9, while arrays.asList has been available since Java 1.2. We can use list.off for read-only constant data. Choose arrays.asList when you need an editable view of an existing array without adding or removing elements. Let's move to next question. How do virtual threads improve concurrency performance? Traditional threads use a one-to-one mapping with operating system threads. Each Java thread ties up an entire OS thread, making them heavyweight and resource-intensive, with high stack memory usage and costly context switches. If a task is blocked, such as waiting for I/O, the OS thread is stuck until it finishes. This approach limits scalability, especially for applications needing lots of simultaneous connections. On the other hand, Project Loom introduced lightweight virtual threads, managed by the JVM. Multiple virtual threads are mapped onto a smaller pool of OS threads using the fork join pool. When a virtual thread blocks, such as during I/O, it is simply suspended and unmapped from the OS thread, freeing up resources for other virtual threads. This enables high concurrency as millions of tasks or connections can be handled efficiently with reduced overhead. What makes virtual threads better? Their lightweight nature allows a massive number of threads with a low memory footprint. They make high concurrency easy, efficiently handling millions of connections. Resource overhead is minimized with less context switching and better CPU utilization. Virtual threads are ideal for server scenarios that require high throughput and low latency, like web servers and microservices managing thousands of simultaneous clients. By enabling non-blocking I/O and efficient request handling, throughput increases while latency drops. Let's move to next question. Describe how switch expressions with yield work in Java 14+. Before Java 12, the switch statement was verbose and stateful. You had to assign results to external variables and remember to include break statements to prevent accidental fall-through. Mistakes like missing break were common, and values from the switch block weren't directly returned. They needed manual assignment outside the block. With Java 14, switch expressions allow direct value return using yield. This concise and functional approach reduces errors like fall-through and enables immutable expression-based code by default. Instead of mutating external state, the switch result can be assigned to a variable, passed as a method argument, or used in expression chains. If we compare both, traditional switch statements mutate external state, require extra boilerplate and break statements, can't be used directly as expressions, while switch expressions with yield produce a final value directly, eliminate the need for break, fit cleanly into larger expressions and method calls, enforce exhaustiveness checks in many cases, improving reliability. Let's move to next question. What are the use cases for completable future and how does it help in async programming? Starting with non-blocking operations. With completable future, you can download files or process large datasets without blocking the main thread. API network calls are made without waiting, and CPU-bound tasks are offloaded, improving overall performance and responsiveness. Completable future enables fluent future chaining or pipelines. You fetch data asynchronously, transform it, then save or finalize the result. Each stage executes in sequence without blocking, building efficient and scalable workflows. You can execute multiple independent tasks in parallel. Use completablefuture.all to join results from different tasks, which reduces overall time by running tasks concurrently and delivering a combined result faster. Don't forget error handling. With completable future, you use exceptionally and handle to gracefully manage errors, recovering and completing tasks without crashing the application. Outcomes are checked with then apply or then accept, ensuring robust error recovery and final state management. Let's move to next question. How does instance of pattern matching enhance type safety in Java 16+? Before Java 16, checking an object's type involved two steps. First, you checked the type using instance of, then performed a manual typecast like string object. This approach made code verbose, increased error risk, and required double-checking type safety. Now with pattern matching, Java combines type check and cast in a single step. If object instance of string str. If the type matches, the variable is automatically cast and available for use. This concise syntax leads to safer, clearer code with less room for mistakes. Benefits of switching to pattern matching. Simplifies type checks and conditional logic. Automatically casts, removing the need for manual casting. Reduces the chance of errors and makes code easier to read and maintain. Let's move to next question. What are some new string methods introduced in Java 11 Plus? Let's review 4 powerful string functions introduced in Java 11 and newer versions, making code cleaner, more expressive, and easier to write. The strip method robustly removes all leading and trailing whitespace, including Unicode spaces, from a string, unlike the older trim, which couldn't handle certain Unicode characters. This results in more reliable whitespace cleanup. IsBlank checks if a string is empty or contains only whitespace, giving a straightforward way to validate blank input. Previously, you'd use isEmpty, which didn't catch strings with just spaces. Now, isBlank returns true for any string with only whitespace. The lines method splits a multi-line string into a stream of individual lines, which enables efficient, lazy processing of each line. With older Java versions, this required manually splitting strings and handling line endings. Now it's both concise and high performance. Repeat count lets you repeat a string a given number of times. Before Java 11, you'd need a manual loop to duplicate a string, but now you can do this with a single line, making pattern creation easy and reducing boilerplate. With these new methods, Java strings are easier to process and validate, helping developers write clean, efficient, and readable code. Let's move to next question. How does map.off behave with duplicate keys? When using map.off, you create an immutable map object where all keys must be unique. For example, here map.off creates a map with 3 unique keys, each mapped to its corresponding value. But if you try to include duplicate keys, such as this, Java immediately throws an argument exception at runtime. No map is created, and this exception makes it clear that duplicate keys are not allowed. The key takeaway is that map.off strictly enforces the uniqueness of keys. Any attempt to use duplicate keys will result in an exception, not silent overwriting as seen in some other map implementations. That's the end of video. Do subscribe for more such interview question and answers.